So this presentation's on conditional probability, the law of intersections, and independent events. And this material is in modules 9 and 10 in the OLI textbook, and it's modules 8 through 10, topic 3 on the logic of events in the workbook. And so here's the situation. We've got some flowers in a field, and we're going to select a flower at random. And L is the event that a large flower is selected, or you can think that L is the set of large flowers. R is the event that a red flower is selected. And the model we're using is that all the flowers are equally likely to be selected. Now this figure that I've drawn here is called a two-way table. I'm going to put the number of large red flowers right here in the large column in the red row. And so there are these two flowers that are the capital letters. Those are the large flowers, and they're red. So I've got two large red flowers, and then red flowers that are not large. I have these two lowercase small red flowers. So the total for that row is there's 4 red flowers. And then let's see, I've got some large flowers that are not red. Those are the 4 capitalized blue flowers. So 4 large, not red flowers. And then the flowers that are neither red nor large, it's these 2 lowercase blue flowers. So that's 2 of those. So 4 flowers that are red, 6 flowers that are not red, a total of 10 flowers in the field. Of those 10 flowers, 6 of them are large, 4 of them are not large. So I filled in my two-way table. All right, now I can use this to illustrate this idea of conditional probability. So I'm going to write an expression here for the probability that a flower is large given that it's red. Okay. So let me write down how you pronounce that. Probability of L given R. So what that means is, well, imagine you wander around in the field and you get a flower, you're blindfolded, you don't know what kind of flower you got. And then I tell you, it was a red one. Now what's the probability that it's large if you're given that additional information? And so what that does is it just changes the denominator. See, if I didn't give you that information, you'd say, what's the probability that it's large? Well, you count the large ones. There's 6 large ones, divided by 10 flowers in all, so probability that it's large is 6 over 10. Okay, but this is saying, no, it's not 10 in the denominator because I've told you already it was a red one. So now you know it's one of those 4 red flowers. Now what's the probability that it's large? Well, of those 4 red flowers, two of them are large. Those were the large red flowers. It's these ones right here in the red row and the large column. See, to get those two large red flowers, what's the event that I counted? It was the intersection of large with red. Okay, so the probability of getting a large flower was 60%. But then if I tell you it's red, now the probability is 50%. Being given that information changed the probability. Okay. Now, I want to turn this into sort of a general rule that we can use, that we can reuse. So what if I wanted to do this thing, but maybe there are a whole lot of flowers that I can't actually count them. Maybe I just know percentages. Think of it this way, like if I divide the top and the bottom both by the same thing, it's all right, yes. If I do I took the number of large red flowers divided by the number of red flowers, but if I want to, if on the top and the bottom, both, I divide by the total number of flowers, the size of the sample space. See, now what I've got on top is the number of large red flowers divided by the total number of flowers. That's the probability of large red. And on the bottom, I've got the number of red flowers divided by the total number of flowers, size of the universe or sample space. So that's just P of R on the bottom. So why would I want to do that? Well, I might not know how many flowers there are. I just know what percent of all the flowers are large red. Yeah. Maybe I just know the probability. I don't know the actual number of flowers. So, but I can, I can still do this equation. And this thing works. I talked a little bit in the last video about, well, what if it's not like a finite number of flowers? What if you're like throwing darts at a target and there's infinitely many places where the dart could hit on the target? But you could still say, well, the whole target is, 2 square feet of area, and L intersect R is so many square feet, 1 square feet, so 50%. And you can't count the outcomes. You're not counting anything, but you can still make the equation with the probabilities. Okay. And you probably did an algebra class sometime. You could multiply both sides here by P of R. So you get the probability of the intersection of L with R is P of L given R times P of R. These are just two different ways of writing the same equation. Either one, I don't have to give it two separate names, but this is the law of intersections. So let's see how that works out with the numbers up here. So P of L given R was 50%, 0.5. And P of R, there were 4 red flowers out of 10 flowers total. Okay, so let's calculate probability of L intersect R using this formula down here. What I'm doing this for is to show you the language, to show you how it works. Like P of R here, okay, that was 40%. And P of L given R, that was 50%. So what's the 40%? P of R. Saying 40% of the time, you get a red flower. And then when you've got a red flower, 50% of the red ones are large. So 40% of the time you get a red flower, and then half of that 40% of the time, the red flower is also large. So it's 50% of 40% of the time. So what do you get? 0.4 times 0.5 is 0.2. So it's 20% of the time you get a large red flower. And see, if you look up here at the table, that's right. There's 2 out of 10 flowers are large red. So that's the way you think of it. What percent of the time does R happen? And then given that R happens, what percent of those times does L also happen? And that's how you get the probability of L and R both happening. So where people get confused is in a story problem, you get some given information, and sometimes there's trouble trying to tell, are they telling me L given R, or is it that they're telling me L intersect R? It's two different things. And this is that L and R both happen. That's the intersection. And this is that L happens if you're already given that R did happen. Okay. So the probability of L intersect R was the 2 large red flowers divided by the 10 flowers total. But with the L given, it was the 2 large red flowers divided by just the 4 red ones. The difference is the denominator. Okay, now how do you use this equation? You could use it like I did here, where if you know these 2 items, you can figure out that one. But it's an equation with 3 things in it. So if you know any 2 of the things, you could figure out the other one. Now, the one thing to notice here, in this example, P of L was different from P of L given R. Knowing that the flower was red changed the probability that it might be large. Sometimes it might not make a difference. So I've got a definition for you. The two events, A and B, well, let me make this flat here. Okay. Are independent if P of A given B is just the same as P of A given nothing. And P of B given A is just the same as P of B given nothing. So if being told that B happens does not change the probability of A, that's independence. Okay. So in this example, the color and the size of the flowers were not independent. Doesn't mean there's any cause and effect there. It just means the ratios are different. Okay. So we've learned the symbol for conditional probability. We've learned the law of intersections. You can write it two different ways. We've learned the definition of when two events are independent. So we're just almost done. So, this statement here is the general law of intersections. Always works. But if A and B are independent, then P of A given B is just P of A. So in that case, P of A intersect B is just P of A times P of B. Just replace the A given B with plain old A. Common mistake is for people to assume that two events are independent when in fact they're not. And so if you don't have something about the story to make you think that two things are independent, don't use this formula down here. Use the one up top. Okay. So I think that that's all for this topic. I'm going to just write down what we've got so far because from the previous lecture we had P of A union B. It's P of A plus P of B minus P of the intersection. That's the law of unions. Okay. But if A and B are mutually exclusive, so that they can't both happen, the probability of the intersection is 0. So then you get just P of A union B is just P of A plus P of B. So with the intersection you multiply, with the union you add. But here again, the common mistake with the law of unions is to think that two events are mutually exclusive when in fact they're not. Both things could happen with non-zero probability. Okay. So we got the unions, the intersections, and the complements. Probability that an event does not happen is 1 minus the probability that it does. And so this set of probability laws will get you through almost all the problems in the exercises. Now, there are a couple of things that you'll need to know. I'm going to do a separate lecture on something called the law of total probability. So we'll have that one to add to this list. And then I need to show you De Morgan's laws. We'll put that in a separate lecture as well. But then once you have these three things and the two more, then you can solve all the word problems. Okay, so that does it for this presentation.